Hello, so let's start this course, which is like core intuition needed later for machine learning. And please notice that this course is like quick introduction without any minute details or derivations, okay? So let's start with something called scalar. So scalar is just one number, like a is equal to 5, like some variable, or temperature is equal to 23, or something like that. And scalar has only magnitude. Vector is an ordered list of numbers, like vector v is equal to 2, 3. So each number is called component. This vector has two components, and the dimension of a vector is the number of its components. So this vector has two. So each vector is two-dimensional vector. And if vector has like three components, 1, 2, 3, it's three-dimensional vector, and so on. And vector answers the question not only how much, like scalar, but in which direction. So like imagine you moved 5 meters right, and this is a vector, like this land 5 meter, and the direction right, okay? And if we build some coordinate plot, 2D dimensional, for vector 2, 3, that means that we move some point from the origin of coordinate system by 2 units across the x-axis and 3 units across the y-axis. So to this point, 2, 3, and the vector is the arrow to this point, okay? And here we have something called vector space. Vector space is a set of vectors where we can add vectors and multiply vectors by scalars and still remain inside the same space. So imagine we have vectors here 1, 2, and vector v 2, 3, 3, 4, for example. And if we add these vectors, u plus v, we just add each component individually, like 1 plus 3 and 2 plus 4, so it's equal to 4 and 6, okay? And if we multiply the vector with some scalar, like 3u, then we need to multiply each component of u by the scalar, so we have 3 by 1 and 3 by 2, so it's like 3 and 6. Okay, so both results are still a second dimensional vector. So the 2D plane is a vector space. Okay, and here we have something called linear combination. Means combining vectors using scalar weights. So if we have like two vectors u and v, and we multiply each by some weights, like alpha multiplied by u plus beta multiplied by v, then this is called linear combination. We just add two vectors, each of which is multiplied by some scalar, okay? So for example, 3 multiplied by u plus 4 multiplied by v is linear combination, and is equal to, in case of, let vector u be 1, 0, and v 0, 1. So 3u is like just 3, and plus 4v is like 4, okay? 3, 4. So linear combination means take some amount of one direction plus some amount of another direction. Let's build this vector on coordinate space, coordinate system. So we have vector u, which is 1, 0, and coordinate vector v, which is 0, 1, okay? And 3u is vector like that. And 4v is vector like that, okay? And you can see that these vectors are pointing in different direction. And if we add them together, we have new vector in pointing to the 3, 4 from the origin. So we take some direction from vector 4v and some direction of vector 3u and got some new completely different direction. Let's call it like that, okay? Okay, and let's move to the span. So span of a set of vectors is the set of all vectors we can create using their linear combinations. So for these two vectors, 1, 0 and 0, 1, their span is the whole 2D plane, because we can create any vector by a linear combination of these two vectors. Okay, so for example, if we take some vector 5 minus 2, we can create this vector by combining 5 multiplied by vector u, like 1, 0, plus minus 2 multiplied by 0, 1. So we just represented this vector as a linear combination of vector u and v, and this works well for any vector in 2D space. Like we can write any vector like x and y is equal to just x multiplied by 0, 1, which give us x0 plus y multiplied by 0, 1, which give us 0, y. And when we add them up, we have xy, okay? So that means that all the whole 2D plane is span of these two vectors, okay? And if we have like vectors like 1, 0, and 2, 0, then both vectors point along the same line, like in coordinate system. You can see the vector, this vector u and this vector v, okay? And it's example wherein the span is not the whole 2D plane, but only x-axis. So we can represent, with these two vectors, we can represent only vectors that are aligned on the x-axis, so x0, okay? And after that, we have something called linear independence. So vectors are linearly independent if none of them can be created from the others. So these two vectors we had before, 1, 0, and 0, 1, are linearly independent because we cannot create vector v by scaling vector u. So there is no such scalar, okay? But in example of these two vectors, they are linearly dependent because vector v is just vector u multiplied by scalar 2, okay? So that's why they are dependent. And we can think about that like linear independence means that each vector brings new direction, as we shown on previous plot over here, okay? But dependence means that some vector is redundant, unnecessary. Like this vector v is not needed to represent any other vector because it's the same as vector u, just multiplied by some scalar. Hope it makes sense. Okay, and let's move to the basis. So basis is just a set of vectors that is linearly independent and spans the whole space. So what does it mean? Like for two-dimensional space, we have two basis vectors, e1 and e2, which is equal to 1, 0 and 0, 1. It's not only possible combination of basis vectors, but let it be. And we can describe any possible vector of this 2D space with linear combination of these two basis vectors. So that's why whole 2D space is span for these two vectors. Like that's why I said it spans the whole space, okay? And there must be linear independent because only linear independent vectors can recreate any other vector in space. I mean, with in previous example where I showed that u and v are linearly dependent, like in this 2D space, you can see that we cannot represent vector like that with these two vectors because they are linearly dependent, and we can represent only x-axis vectors. Okay, so vectors must be linearly independent, like in example like that, where we have two vectors in different directions and they are linearly independent, so we can represent any vector. Okay, and what does that mean? What does it mean? So we have like points 3, 4 in this space, vector 3, 4, and we just can represent this vector as scalar 3 multiplied by basis vector e1 and plus scalar 4 multiplied by e2. Okay, so any 2D vector can be built from them. And it's important to note that the same geometric vector can have different coordinate values if we use different bases. And for each vector, we can measure the length or like magnitude of a vector, and it's called norm. And Euclidean norm for some vector which is equal like xy is noted like z. Y is equal to square root of squared sum x squared plus y squared. Okay. For example, we have vectors 3, 4, and then it means 9 plus 16 under square root. So it's equal to square root of 25, which is 5. Okay, so the length of this vector is 5. And it doesn't matter what is the dimension of vector, like for vector of n dimensional, we have like v1, v2, v3, and so on to vn's. So Euclidean norm will be equal to just square root of each squared components. Okay. And norm answers how long is this vector and like how large is this object in vector form. Okay. And if we have two vectors, we can measure the distance between them. And the distance between two vectors is the norm of their difference. So we just need to, if we have like two vectors, so distance of two vectors u and v, it's equal to just norm of difference of these two vectors, okay? And if we have example vector is equal to 1, 2, and vector v is equal to 4, 6, then the difference is equal to 3, 4. And the norm of this difference is equal to square root of 3 squared plus 4 squared, so it's 5, square root of 25. Okay? So the distance, like how far apart are these two vectors, is equal to 5 in our case. And we can visualize this distance, so we can build some coordinate system. And vector u is 1, 2, so somewhere here, and vector v is 4, 6, so in this place, somewhere here, okay? And the distance is the vector from the end of vector u to the end of vector v, so it's vector like that, okay? And as we said before, the length of this vector is the norm, but it's derived from Pythagoras theorem, so it's like right angle triangle, and you can calculate each side of this triangle. Like we have 4 units across y-axis and 3 units across x-axis, which is our actually difference between these vectors, yes? And by this Pythagoras theorem, we know that the side opposite to the 90-degree angle is equal to the squares of each of the other two sides added together. So that's why we have this formula, so it's equal to 5, okay? Moving on, dot product. So the dot product takes two vectors of the same dimension and returns one scalar. Dot product, okay? So we have like vector u, which is equal to u1, u2, and v, which is equal to v1, v2. So the dot product is not like that, and it's equal to u1 multiplied by v1 plus u2 multiplied by v2. So it's like algebraic interpretation. And if we have numbers like 1, 2, 3, 4, then it's equal to 1 by 3 plus 2 by 4, so it's 11. And also have some geometrical meaning, geometrical interpretation, and the formula is the same, but just in different terms. So it's like the length of u multiplied by the length of v and multiplied by the cosine of the angle between them. Okay, and what does this number mean? To understand that, we need to understand geometric meaning. So the dot product measure how much two vectors point in the same direction. Okay, let's get a cosine from this formula. So cosine is equal to v dot product divided by the length of each vector, right? And to understand how it works, let's build some coordinate system. So imagine you have two vectors and some angle between them, okay? So As I said, dot product show us the direction, like of this can help us to understand either our vector are in the same direction or pointing in the same direction or perpendicular or in opposite direction. Yeah. So to understand that, let's build some unit circle. And what is cosine? Like from geometrical meaning, cosine on the unit circle is x-axis, right? So if we have some angle like that, then cosine is this number, like 0.6, right? So when the vectors are perpendicular, so vectors are perpendicular when the theta, the angle between them, is equal to 90 degrees, okay? And on this plot, we can see that this angle gives us cosine equal to 0. So when the dot product is equal to 0, it means that vectors are perpendicular. Okay? When the angle is equal to, for example, 0 degrees, that means that these two vectors are pointing in the same direction, right? And in this case, cosine is equal to the 1. So when we have large positive dot product, that means that these vectors have similar direction. And if cosine, like the angle between them, is equal to 0, they're pointing in the exact same direction. Okay? And if theta is equal to 180 degrees, that means that they are pointing in opposite direction. So it's something like that. And then cosine is equal to -1. So cosine of 180 is equal to -1. So when dot product is negative, we have opposite direction. And when angle is equal to 180, then the direction is like the same, exact the same, but in opposite way. So it's like that, right? And the angle is 180. And in machine learning, in future courses, you can see some term called cosine similarity. And cosine similarity measures similarity by angle, not by length. So, and actually, it's just this cosine formula, like cosine of some angle theta, so cosine of between some vectors, is our cosine similarity, and it's equal to just dot product divided by length of each vector. And if cosine similarity gives us some value equal to 1, we have same direction of vectors. When 0, as we discussed, that means that vectors are perpendicular, and when -1, opposite direction, right? And for example, if we have vector like 1, 0, and 2, 0, it's pretty obvious to understand that they are pointing in the same direction, but we can put it to the formula. So cosine of theta is equal to dot product 1 by 2 plus 0 by 0 divided by 1 squared under the root multiplied by 2 squared under the square root. So it's equal to 2 divided by 2.